Okay, this video is going to be about centripetal force. This is something that we studied a little bit last year and you should know about, but here's some concepts that maybe review or maybe new. So let's just start out with an example. Let's say we've got a road with a curve in it and we're looking from the top down. So there's a road with a curve in it and we've got a car traveling down the road. There's my car, pretty simple. What we know from Newton's first law is that if the car is moving, then it's going to want to keep going in a straight line unless there's a force acting on it. So if I want to get my car to turn to the right to go around this corner here, what I need is a force acting on it in this direction to get it to turn. And maybe a little bit further down the road, here's the car. Once again, Newton's first law says it wants to keep going in this direction. So we need a force to make it turn to the right. And there we go. And you can keep going around the corner. Wherever you are, the force is going to be pointing towards the center. So that's what centripetal is going to mean, is towards the center. That means centripetal. So you need a force towards the center of the circle in order to go around the circle. Otherwise, you'll just keep going in a straight line. So there's a formula for centripetal force. That's Fc. Centripetal force is mv squared over r. You can also just describe the centripetal acceleration as v squared over r. Right? Let's do a quick example. Let's put some numbers in. Example. Let's say that you have a car with a mass of 1,000 kilograms and it's going at 20 meters per second and the radius of the corner is 50 meters. Now these would be things that would be given to you in a problem, or you may figure them out from another place. And now let's figure out what's the centripetal force on the car as it goes around the corner. Right, so we have Fc equals 1,000 kilograms times 20 meters per second squared divided by 50 meters, and that turns out to be 8,000 newtons. Now remember, your units for newtons in here, newtons are actually kilograms meters squared per second squared, right? So just check out, meters per second squared, right? That would have been energy units if this would have been meters squared, but just kilograms meters per second squared. So just check out that that actually works out. There's my kilograms. This would give me meters squared, but then that takes away the meters from down there and then divided by second squared on the bottom. So it works out for the units. Just make sure you're in kilograms, meters per second, and meters, and it should work out. Right? Let's do another example. Let's say that I've got a ball that's attached to a string, and then this is a view from above, looking down. Looking from above. So I don't want to involve gravity right here. And I'm just swinging this ball around in a horizontal circle, right? Just going around and around in a circle. So we're looking down from above. And I'll just put some numbers in here. Let's say that the radius of the length of the string is, I don't know, half a meter. And let's say the ball is going with a speed. Actually, let's change this around a little bit. Let's say that what we know about the ball is that it's going at 100 revolutions per minute. That'll just make one more extra calculation that we need to do. And then I need to know the mass of the ball. So let's say the mass of the ball is, 2 kilograms or something like that. And what I maybe want to do is I want to find out what's the tension in the string, because I want to know if I swing it too fast, is the string going to break? Is the string not going to break? Maybe that's what my question is. So if I draw a free body diagram of the ball, it's pretty easy. There's the ball. There's only one force acting on the ball, and it's tension right there. Right? Now keep in mind that you when you're spinning something around in a circle, you feel a fictitious force pulling out, but right, that's not actually really a force. That's what they call sometimes centrifugal force. Centrifugal. That's away from the center. That's not actually really a force. The only force acting on the ball is that tension right there. So if I want to write a net force equation, F net equals ma, I know that this acceleration is v squared over r. So I can write this as mv squared over r, right? And then this just turns into tension equals mv squared over r, right? Now part of the trick is, how can I figure out what my v is? Let's do that over here. If I want to find v, then I can start out with 100 revolutions per minute, and I want to multiply something that gets revolutions on the bottom and meters on the top, right? So how do I get how many meters are in one revolution? Well, that's just one circle. So that's going to be 2 pi r meters per one revolution, right? And that'll cancel out my revolution units. This is just kind of what they do in chemistry, right? And then I want to get something with minutes on the top and seconds on the bottom. So what am I going to do? Well, that's going to be 60 seconds is 1 minute, right? And if I work this out and plug the numbers in, remember r is half a meter. So if I plug half a meter in right there, then what I'll get out of this is, this turns out to be, I did this before, 5.2 meters per second, right? Now I just need to start plugging things in, and I'll leave you to do that. Here's my v, stick in v there. I know what my m is, and I know what my r is, and if you do this all out, like I said, I'll leave you to do it because I'm running out of space. This turns out to be 108 newtons, and that's the tension in the string. And next video, we'll just do another couple of examples of centripetal force.